Tonight we're going to explore something that sounds deceptively simple: a light year. You've heard this term countless times. Scientists use it constantly when discussing space. But here's what most people don't realize. When you truly understand what a light year represents, when you grasp the actual distance it describes, it fundamentally changes how you see your place in the cosmos. It's not just a large number. It's a distance so vast that it breaks our ability to comprehend it. And that breaking point reveals something profound about the universe we inhabit. Let me start with something familiar. You understand distance in your everyday life. You know how far it is to your workplace, to the nearest store, to the next city over. These are distances you can relate to because you've traveled them. You have a sense of what they mean in terms of time, in terms of effort, in terms of what you'll see along the way. A kilometer is about the distance you can walk in 10 to 12 minutes at a normal pace. These measurements work perfectly well for human-scaled experiences. If someone tells you the store is 5 kilometers away, you know roughly how long it'll take to drive there. You can picture the journey in your mind. Maybe you'll pass a few traffic lights. Maybe you'll see some familiar landmarks. The distance is concrete and relatable, but these familiar measurements start to become awkward when we talk about truly large distances. The distance from New York to Los Angeles is about 4,500 kilometers. That's still manageable as a number. It's about a 5-hour flight. People make that journey regularly. They cross the continent. They see the landscape change from East Coast cities to Midwest plains to Rocky Mountains and finally to the Pacific coast. The journey is long, but it's achievable. It's within human capability. The Earth's circumference at the equator is about 40,000 kilometers. That's a big number, but it's still something we can work with conceptually. Early explorers sailed around the world, so we know it's possible to travel that distance, even if it takes months. The Earth is large from our perspective standing on its surface, but it's not incomprehensibly large. It's a finite thing you could theoretically explore completely. But now, let's go bigger. The distance from Earth to the Moon is about 384,000 kilometers. This is where normal measurements start to feel inadequate. You can't visualize 384,000 kilometers in any meaningful way. It's not like driving across the country. It's not like sailing around the world. It's something completely different. How would you even begin to travel that far? The Apollo astronauts took about 3 days to travel from Earth to the Moon using powerful rockets. 3 days of traveling through empty space at speeds no human had ever experienced before, just to reach our nearest celestial neighbor. And that's just to the Moon, which you can see hanging in the sky every night. When we start talking about the distance to other planets, to the Sun, to other stars, kilometers become completely useless. The numbers get so large that they lose all meaning. They become abstract symbols rather than distances you can relate to in any way. The distance from Earth to the Sun is about 150 million kilometers. Try to visualize that. You can't. Your brain just sees it as a really big number, but you don't have any intuitive sense of what it means. There's nothing in your daily life that prepares you for a distance like that. We didn't evolve to comprehend 150 million kilometers. The Apollo spacecraft that took astronauts to the Moon traveled at about 11 kilometers per second on average. At that speed, it would take about 160 days to reach the sun, over 5 months of constant travel at incredible speed just to cover the distance to our own star. And the sun is close. It's right here in our cosmic neighborhood. It's the source of all the light and heat that makes life on Earth possible. We see it every day. And yet, it's 150 million kilometers away. When we start talking about distances to other stars, even the sun's distance becomes tiny by comparison. The sun is our nearest star, and it's 150 million kilometers away. The next nearest star is about 266,000 times farther than that. 266,000 times farther than a distance that already takes our fastest spacecraft months to cover. This is why astronomers needed a different unit of measurement. Not because they like making things complicated, but because kilometers simply don't work when you're measuring cosmic distances. Using kilometers to measure distances to stars would be like using millimeters to measure the distance between countries. Technically possible, but completely impractical. So astronomers came up with something different, the light year. And here's what you need to understand right from the start. A light year is not a measure of time. I know it has the word year in it, which makes it sound like time, but it's not. A light year is a measure of distance. It's the distance that light travels in 1 year. Now, why base a measurement on light? Because light is special. Light is the fastest thing in the universe. Nothing can travel faster than light. It's not just a speed limit that we haven't broken yet. It's a fundamental law of physics. The speed of light is constant, unchanging, the same everywhere in the universe. Light travels at about 300,000 kilometers per second. Every single second, light travels 300,000 kilometers. That's incredibly fast. To put it in perspective, light can travel around the Earth's equator about 7.5 times in 1 second. In the time it takes you to snap your fingers, light could circle the entire planet multiple times. It's a speed that's almost impossible to visualize, because nothing in our everyday experience moves anywhere near that fast. The fastest thing most people experience is an airplane. A commercial jet flies at about 900 kilometers per hour. Light travels over 1 million times faster than that. When you turn on a light switch, the light reaches your eyes essentially instantly because the room is so small. But the light did travel. It took time. It's just that the time was so short, you couldn't possibly notice it. When you see the sun in the sky, you're actually seeing it as it was 8 minutes and 20 seconds ago, because that's how long it takes light to travel from the sun to Earth. The sun is so far away that even light, traveling at 300,000 kilometers per second, needs over 8 minutes to cover the distance. This has an interesting implication. If something happened on the sun right now, we wouldn't know for over 8 minutes. The event would happen, but the light carrying information about that event would still be traveling toward us. When you look at the moon, you're seeing it as it was about 1 3/10 seconds ago. When astronauts walked on the moon and talked to mission control on Earth, every word they spoke took 1 3/10 seconds to reach Earth, and every response from mission control took 1 3/10 seconds to reach the moon. You can hear this delay in the recordings. There's always this pause because the radio signals carrying their voices traveled at the speed of light. Light doesn't travel instantly. It has a speed, and that speed, while incredibly fast, is still finite. So a light year is the distance light travels in 1 year at this speed. Let's calculate that. Light travels at 300,000 kilometers per second. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. If we multiply all of these together, we get approximately 9.46 trillion kilometers. That's what a light year is. 9.46 trillion kilometers. Not a measure of time, but a measure of distance. The distance that light, the fastest thing in the universe, travels in 1 year. And that's the number we're going to try to understand. Because understanding what a light year means is essential to understanding our place in the universe, the distances between stars, and the true scale of the cosmos. But first, we need to talk about what a trillion actually means, because most people have no intuitive sense of how large this number really is. We throw around words like million, billion, and trillion in everyday conversation, but the differences between them are staggering. A million is 1,000 thousands. If you saved $1 every day, you'd have $1 million in about 2,740 years. That's a long time, but it's conceivable. You can imagine a timeline stretching back 2,740 years. A billion is 1,000 millions. If you saved $1 every second, you'd need about 32 years to save $1 billion. That's more than the time it takes for a generation to grow up. 1 million seconds is about 11.5 days, but 1 billion seconds is 32 years. A trillion is 1,000 billions. If you counted to a trillion, counting one number per second without stopping, it would take you about 31,700 years. That's longer than all of recorded human history. Agriculture was only invented about 10,000 years ago. Writing systems appeared about 5,000 years ago. To count to a trillion, you'd need to have started counting before any of that happened. And a light year is 9.46 trillion kilometers. Every single one of those kilometers is a real distance. The distance you could walk in about 10 to 12 minutes, and there are 9.46 trillion of those individual kilometer-long segments in one light year. The best way to understand a light year is to build up to it gradually, starting with distances we can comprehend and scaling up step by step. Let's start with 1 light second. 300,000 kilometers. That's about the distance from Earth to the Moon and 3/4 of the way back. 1 light minute is 60 light seconds, 18 million kilometers. The Sun is about 8 light minutes away from Earth. 1 light hour is 60 light minutes. That's about 1,080,000,000 kilometers. The planet Saturn is about 1.2 light hours away at its closest approach. 1 light day is 24 light hours, about 25,900,000,000 kilometers. This is roughly the distance to the edge of our solar system. 1 light week is 7 light days. 1 light month is roughly 30 light days. And 1 light year is 365 light days. See how quickly the numbers scale up. We started with 1 light second, which was already an enormous distance by human standards, and we've been multiplying by larger and larger numbers. And we're just now getting to 1 light year, 9.46 trillion kilometers. And this is the fundamental unit astronomers use to measure the distances between stars, because stars are separated by distances measured in light years, and nothing smaller makes sense when you're dealing with these vast cosmic scales. As you listen, notice how difficult it is to actually picture this. Your mind might accept the mathematics, but it struggles to truly visualize what 9.46 trillion kilometers means. This isn't a failure of imagination, it's a natural limitation of human cognition, encountering scales that exceed our evolutionary experience. So why is this limitation so fundamental? It's not just that the numbers are big, it's that they exceed the computational capacity that evolution built into our brains. For millions of years, our ancestors needed to estimate distances they could walk in a day, count the members of their tribe, track animals across familiar terrain. Natural selection optimized our minds for scales that mattered for survival. We can intuitively grasp dozens, maybe hundreds of objects. We can imagine distances measured in days of travel, but 9.46 trillion of anything? Our neural architecture simply wasn't designed for that. This creates something interesting, a kind of cognitive horizon beyond which numbers lose their intuitive meaning and become pure abstraction. And light years live far beyond that horizon. Let's try a different approach. Instead of thinking about the distance itself, let's think about what it means to travel at the speed of light. Because even light, the fastest thing possible, needs an entire year to cover 1 light year. Imagine you could somehow travel at light speed. You leave Earth and head toward Proxima Centauri, our nearest stellar neighbor, 4.24 light years away. Even moving at the ultimate speed limit of the universe, you'd be traveling for 4 years and 3 months. 4 years of continuous motion through the void. No stops, no rest. Just 4 years of crossing empty space at 300,000 kilometers every second. But here's where it gets strange. Due to the effects of relativity, if you were somehow traveling at light speed, you wouldn't experience those 4 years passing. Time would effectively stop for you. From your perspective, the journey would be instantaneous. You'd leave Earth and immediately arrive at Proxima Centauri. But from Earth's perspective, watching you go, 4.25 years would pass. Your friends would age, seasons would change, children would grow, and you'd still be traveling through the darkness. This isn't science fiction. It's the actual structure of space and time as physics understands it. The universe imposes this strange trade-off. Travel fast enough, and time slows down for you relative to everyone else. But you can never quite reach light speed if you have mass. You can get close, very close, but never quite there. The energy required approaches infinity as you approach light speed. So even our hypothetical journey at light speed is impossible for anything with substance, anything real. Real spacecraft, carrying real people or instruments, travel much slower. The fastest human-made object, the Parker Solar Probe, reaches speeds of about 700,000 kilometers per hour when it's closest to the sun. That sounds incredibly fast, but it's only about 0.06% the speed of light. At that speed, it would take roughly 75,000 years to reach Proxima Centauri. 75,000 years. That's longer than modern humans have existed. Our species is only about 300,000 years old. Agriculture began about 12,000 years ago. Civilization, as we know it is perhaps 6,000 years old. A journey to our nearest stellar neighbor would take longer than all of human recorded history. And Proxima Centauri is close, unimaginably close by cosmic standards. It's right next door. Most stars are much, much farther away. Sirius, the brightest star in our night sky, is 8.6 light years away. Vega, another bright star, is 25 light years away. The center of our galaxy is 26,000 light years away. The nearest large galaxy, Andromeda, is 2.5 million light years away. 2.5 million light years. Light traveling continuously for 2.5 million years covers that distance. 2.5 million years ago, our ancestors were just learning to use stone tools. They were barely recognizable as human. They had no language as we understand it, no art, no permanent settlements. They lived in small groups, struggling to survive in a world of predators and changing climates. The light you see from Andromeda Galaxy tonight began its journey when those primitive ancestors were chipping rocks into crude implements. That light has been traveling through space for all of human evolution. It crossed the void while our species developed language, built civilizations, discovered science, and began to understand the very stars that produced that light. And Andromeda is still considered nearby in cosmic terms. It's part of what astronomers call the local group, our galactic neighborhood. Beyond that, distances become even more staggering. The observable universe, the sphere of space from which light has had time to reach us since the beginning of everything, is about 93 billion light years across. 93 billion light years. That's the distance light could travel in 93 billion years if the universe weren't expanding. But the universe is expanding, stretching space itself, which makes the calculation more complex. The edge of the observable universe represents regions that are now much farther away than 93 billion light years, because space has been stretching while that ancient light traveled toward us. This expansion creates another layer of strangeness. Galaxies beyond a certain distance are moving away from us faster than light could travel to reach them. Not because those galaxies are moving through space faster than light, which would be impossible, but because space itself is expanding fast enough to carry them beyond our reach. There are galaxies out there whose light will never reach us, not because they're dark, but because the expansion of space creates a horizon beyond which communication becomes impossible. These galaxies exist in a kind of cosmic isolation, forever cut off from our observational reach. The universe is not only vast, it's also structured in a way that imposes fundamental limits on what we can know about it. As you listen, notice how these scales begin to accumulate. We started with familiar distances, moved to planetary distances, then stellar distances, then galactic distances, and now cosmic distances. Each step represents a leap in scale so large that the previous distances become negligible. The distance from Earth to the Moon, which seemed impossibly large when we first considered it, is now smaller than a pixel in this cosmic picture. The distance to the Sun, 150 million kilometers, becomes a point. The distance to Proxima Centauri, our nearest star, becomes a short step. Our entire galaxy, 100,000 light years across, becomes a small island in an ocean of space, and this scaling continues. what we call the local group, containing dozens of galaxies, including our Milky Way and Andromeda, spans about 10 million light years. It's a gravitationally bound collection of galaxies, all orbiting their common center of mass in a slow cosmic dance that takes billions of years to complete. But the local group itself is just one small structure in something larger called the Virgo supercluster, which spans about 100 million light years. The Virgo supercluster contains thousands of galaxies arranged in groups and clusters, all connected by gravity across these enormous distances. And even the Virgo supercluster is just one structure among many. Recent observations have revealed that superclusters themselves are arranged into even larger structures called galaxy filaments, vast threads of matter stretching across hundreds of millions of light years. Between these filaments are cosmic voids, regions of space that are nearly empty, where galaxies are rare and the density of matter is much lower than average. The largest known structure in the universe is something called the Hercules Corona Borealis Great Wall, a galaxy filament that stretches about 10 billion light years across. 10 billion light years. That's roughly 1/9 the diameter of the entire observable universe. Think about that for a moment. A single structure made of galaxies and dark matter that spans 10 billion light years. Light takes 10 billion years to cross it. When that light began its journey, the universe itself was only about 3.5 billion years old. The Sun and Earth didn't even exist yet. This is where our exploration of light years leads us. Not just to an understanding of distance, but to a recognition of structure and scale that defies human intuition. We live on a planet orbiting a star in a galaxy that's part of a group, that's part of a supercluster, that's part of a filament in a cosmic web that spans the observable universe. And this entire structure, everything we can see or detect or theorize about, might be just one region in a much larger or even infinite universe that extends far beyond our observational reach. The light year, that simple unit of distance, becomes a tool for navigating this hierarchy of scales. It's not just a measurement. It's a bridge between the human-scaled world we inhabit and the cosmic-scaled universe that contains us. But there's something else that light years reveal, something perhaps even more profound than scale. They reveal the relationship between space and time in our universe. When we measure distances in light years, we're simultaneously measuring time. The two become inseparable. When you look at a star 10 light years away, you're seeing it as it was 10 years ago. You're not just looking across space, you're looking back in time. The universe becomes a kind of time machine where distance and temporal displacement are the same thing. This means that astronomy is fundamentally a historical science. Every observation is an observation of the past. The farther we look, the further back in time we see. Telescopes don't just show us distant objects, they show us ancient objects, the universe as it was at different epochs. The most distant galaxies we can observe appear as they were when the universe was very young, perhaps only a few 100 million years old. These galaxies look different from modern galaxies. They're smaller, more irregular, actively forming stars at rates much higher than galaxies today. We're seeing the universe in its youth, when conditions were different, when the first stars were still forming, when the large-scale structure we see today was just beginning to emerge. This temporal aspect of light years creates a strange situation. The universe we observe is not the universe as it exists right now. It's a patchwork of different times, with nearby objects showing us the recent past, and distant objects showing us the ancient past. We never see the universe as it is right now, only as it was. And because the universe is expanding, those distant galaxies we see in their ancient state are now much farther away than the light travel time suggests. A galaxy whose light took 10 billion years to reach us has been carried away by cosmic expansion during that time. It's now perhaps 20 billion light years away, far beyond the distance its light travel time would indicate. The universe is not only larger than it appears, it's also older than it appears at any given distance. Space and time interweave in ways that make the cosmos simultaneously more complex and more elegant than our everyday experience suggests. This is what light years ultimately teach us, not just about distance, but about the nature of observation itself, the structure of space and time, and our place as observers in a universe that reveals itself only through ancient light carrying messages from the past across distances that challenge the very foundations of human comprehension. The number 9.46 trillion kilometers is just the beginning. It's a doorway into a universe stranger and more beautiful than our intuitions could ever have imagined. Let's go deeper into this cosmic isolation, because the speed of light doesn't just limit how fast we can travel, it fundamentally shapes what we can know about the universe at any given moment. Right now, as you listen to these words, events are happening throughout the cosmos. Stars are being born in distant galaxies. Others are dying in spectacular explosions. Black holes are merging, sending gravitational waves rippling through spacetime. Entire civilizations might be rising and falling on planets orbiting other stars. But you will never know about any of it happening right now. The information simply cannot reach you fast enough. The speed of light creates a kind of cosmic censorship, hiding the present state of the universe behind an impenetrable barrier of distance and time. Consider our nearest galactic neighbor, Andromeda, 2.5 million light years away. When you look at Andromeda tonight, you see it as it appeared 2.5 million years ago. If something catastrophic happened to that entire galaxy right now, if every star in it suddenly went dark, you wouldn't know for 2.5 million years. The light carrying that information would still be traveling toward you, crossing the void at the ultimate speed limit. This creates a strange kind of loneliness. We are observationally isolated in the present moment. Every other object in the universe exists in our past. The further away something is, the deeper into the past we see it. We live in a bubble of now that extends only as far as light can travel in an instant. Beyond that bubble, everything is history. But there's something even stranger about this isolation. The universe is expanding. Space itself is stretching. And this expansion means that the light from the most distant objects we can see started its journey when those objects were much closer to us than they are now. A galaxy whose light took 10 billion years to reach us was only about 5 billion light years away when that light began its journey. But during those 10 billion years of travel time, space has been expanding, carrying that galaxy farther and farther away. By now, it might be 20 billion light years distant. The light we see tonight is a message from a galaxy that has since retreated to twice the distance it was when it sent that message. This expansion creates another layer of cosmic censorship. There are galaxies so distant that space is expanding faster than their light can travel toward us. These galaxies are receding at speeds that exceed the speed of light, not because they're moving through space faster than light, which would be impossible, but because space itself is stretching fast enough to carry them beyond our reach. These galaxies exist in a kind of cosmic event horizon. They're real, they're out there, but their light will never reach us. They're being carried away by the expansion of space faster than their light can close the gap. As time passes, more and more galaxies cross this threshold and disappear beyond our observational reach forever. The universe is not only vast, it's actively hiding itself from us. This creates a profound philosophical puzzle. How do we understand a universe that we can never fully observe? How do we comprehend a reality where most of what exists is fundamentally inaccessible to us? Science has developed tools for dealing with this limitation. We use the light we can see to infer the properties of things we cannot see. We measure the cosmic microwave background, the afterglow of the Big Bang, to understand conditions when the universe was only 380,000 years old. We detect gravitational waves from colliding black holes billions of light years away. We study the abundances of light elements to understand nuclear processes that occurred in the first few minutes after the beginning of everything. But these tools have limits. Beyond a certain distance, beyond a certain time in the past, the universe becomes fundamentally unknowable. We approach what cosmologists call the cosmic horizon, the boundary between what we can observe and what we cannot. And this horizon is not fixed. It's growing. Every second, light from slightly more distant regions reaches us for the first time. Our observable universe expands at the speed of light, revealing new territory that was previously hidden beyond the cosmic horizon. But the expansion of space means that even as our observable universe grows, some galaxies are simultaneously disappearing beyond our reach. We're in a race between the expansion of our observable universe and the expansion of space itself. In some directions, we're winning, seeing farther and farther back in time. In others, we're losing, as distant objects are carried beyond our ability to ever observe them. This dynamic creates a kind of cosmic archaeology. The deeper we look into space, the further back in time we see. The most distant galaxies visible to our most powerful telescopes appear as they were when the universe was less than 1 billion years old. These galaxies look different from the galaxies we see nearby. They're smaller, more chaotic, forming stars at rates much higher than modern galaxies. We're seeing the universe in its youth, when conditions were different, when the first generation of stars was still forming, when the large-scale structure we see today was just beginning to emerge from tiny fluctuations in the density of matter and energy. But even this archaeological record is incomplete. There are epochs in cosmic history that we cannot observe directly. The universe was opaque for its first 380,000 years. Light could not travel freely because space was filled with ionized hydrogen that scattered photons before they could travel very far. The cosmic microwave background marks the boundary of this opaque era, the moment when the universe became transparent for the first time. Before that moment, the universe is hidden from us. We can infer what happened using physics and mathematics, but we cannot observe it directly. The first stars, the first galaxies, the details of how structure formed from the nearly smooth conditions we see in the cosmic microwave background, all of this remains partially hidden behind the wall of cosmic opacity. This is what light years ultimately reveal. Not just the scale of distance, but the fundamental limits of observation in a universe governed by the speed of light. We live in a cosmos where distance and time are inseparable, where the present state of distant objects is unknowable, where the expansion of space creates horizons beyond which reality becomes inaccessible. And yet, despite these limitations, the light that does reach us carries extraordinary information. Every photon is a messenger that has traveled for years, centuries, millennia, or billions of years to reach your eye. That light encodes information about the conditions where and when it was emitted, the temperature of the star that produced it, the elements present in the atmosphere through which it passed, the speed at which its source was moving, the gravitational fields that bent its path. When you look up at the night sky, you're not just seeing distant lights, you're receiving messages from across space and time. Each star, each galaxy, is telling you its story, when it formed, how it has evolved, what elements it has created through nuclear fusion, how fast it's moving, whether it has planets, whether those planets might harbor life. The light from our sun tells us that it's a middle-aged star, about 4.5 billion years old, fusing hydrogen into helium in its core at a rate that will sustain it for another 5 billion years. The light from other stars tells us that some are much younger, just forming from collapsing clouds of gas and dust. Others are much older, approaching the end of their lives, destined to explode as supernovas or fade quietly as white dwarf stars. The light from distant galaxies tells us about the expansion of the universe. The farther away a galaxy is, the more its light is redshifted, stretched to longer wavelengths by the expansion of space during its journey toward us. This redshift is proportional to distance, a relationship discovered by Edwin Hubble in the 1920s that revealed the universe is expanding. But the messages carried by light are not just about the objects that emitted it. They're also about the space through which that light traveled. Dark matter, which doesn't emit light but does have gravitational effects, bends the path of light from distant sources. By studying this gravitational lensing, astronomers can map the distribution of dark matter throughout the universe. Gravitational waves, ripples in spacetime itself, carry information about some of the most violent events in the cosmos. The collision of black holes, the merger of neutron stars. These events produce no light, but they shake the very fabric of space and time. The waves travel at the speed of light, carrying information across billions of light years about events that would otherwise be completely hidden from us. Even empty space carries information. The cosmic microwave background, the afterglow of the Big Bang, fills the entire observable universe. This radiation was emitted when the universe became transparent for the first time, about 380,000 years after the beginning. But the tiny temperature variations in this background radiation encode information about the quantum fluctuations that existed in the very early universe, fluctuations that would later grow into galaxies and galaxy clusters. The universe is not silent. It's constantly sending us messages. But these messages take time to arrive. The information encoded in the light and gravitational waves reaching us tonight began its journey years, centuries, millennia, or billions of years ago. We're reading mail from the past, learning about events that happened when the universe was younger, when conditions were different, when the cosmic story was still being written. And this creates another layer of strangeness. The universe we observe is not the universe that exists. It's the universe that existed. We see a patchwork of different epochs, with nearby objects showing us the recent past and distant objects showing us the ancient past. The night sky is a time machine displaying the history of the cosmos, laid out in layers of distance and end time. As you listen, notice how this changes your relationship to the stars. They're not just distant lights, they're time capsules, windows into different eras of cosmic history. Some of the photons entering your eye tonight began their journey before the Earth formed. Others started traveling when the first life appeared on our planet. Still others began their journey when the dinosaurs roamed the Earth, or when the first humans looked up at these same stars and wondered what they were. This temporal aspect of astronomy creates a kind of cosmic archaeology. By looking deeper into space, we look further back in time. We can study the universe at different ages, watching how stars and galaxies formed and evolved over billions of years. We can trace the cosmic story from its earliest observable moments to the present, but we can never see the end of the story. We can never observe the current state of distant objects. We can only see their past. The universe's present moment remains forever hidden from us, locked away behind the cosmic horizon created by the finite speed of light. This limitation shapes everything about how we understand the cosmos. It makes astronomy fundamentally different from other sciences. In chemistry or biology, you can observe systems in real time. You can watch reactions occur, see cells divide, observe evolution in fast reproducing organisms. But in astronomy, everything you observe is ancient history. The laboratory is the past. The experiments have already been run. You can only study the results, transmitted to you across vast distances of space and time. And yet, this limitation has also been a gift. Because the speed of light is finite, because light takes time to travel, we can observe the universe at different ages. We can watch cosmic evolution unfold. We can see how the universe has changed over billions of years. Without this light travel time, we would only be able to observe the universe as it is now. We would have no way to study its history, no way to understand how it evolved from the smooth, hot conditions of the early universe to the rich, complex structure we see today. The finite speed of light turns the universe into its own fossil record. Distance becomes time, space becomes history, and light years become the measuring stick for both. This is perhaps the most profound lesson that light years teach us. They reveal that space and time are not separate. They're woven together into a single fabric that governs everything about how information travels through the cosmos. Einstein called this spacetime, and understanding it revolutionized physics. But you don't need to understand relativity to appreciate its implications. You just need to look up at the night sky and remember that every point of light is a message from the past, traveling across distances measured in light years, carrying information about events that happened when the universe was younger. The stars are not just far away, they're long ago. And in a universe where distance and time are inseparable, that makes all the difference. This creates a strange temporal architecture that most people never consider. When you send a text message to someone across the room, that message travels through electromagnetic signals at the speed of light. The delay is so brief that it feels instantaneous. But when NASA sends commands to a rover on Mars, the engineers must wait anywhere from 4 to 24 minutes for confirmation that the command was received, depending on where Mars sits in its orbit. Mars isn't even that far away in cosmic terms. It's a neighbor, and yet the communication delay makes real-time control impossible. Every decision must be planned in advance. Every response must be anticipated. If something goes wrong, the rover has to handle it alone for those crucial minutes while the radio signals crawl across the solar system at light speed. This is what working with light-year distances really means. Not just vast numbers, but fundamental changes in how cause and effect operate, how information flows, how quickly you can respond to events. Consider what this means for the TRAPPIST-1 system, 7 Earth-sized planets orbiting a small red star 40 light-years away. If there were intelligent life on one of those worlds, and if they had developed radio technology, any signals they broadcast would take 40 years to reach us. By the time we detected their transmission, the civilization that sent it would have aged an entire generation. The children who might have been listening to those first radio broadcasts would now be adults with children of their own. If we replied immediately, our response wouldn't arrive until those children's children were grown. A single exchange of messages would span 80 years. Entire human lifetimes would pass between question and answer. But it gets stranger than communication delays. The expansion of the universe means that space itself is stretching while light travels through it. A galaxy whose light takes 10 billion years to reach us has been carried much farther away during that travel time. When we observe that galaxy, we're not just seeing it as it was 10 billion years ago. We're seeing it from a distance it no longer occupies. Current models suggest that galaxy is now perhaps 20 billion light-years away, carried by the expansion of space to twice the distance it was when it emitted the light we see tonight. The universe has been growing while that ancient message traveled toward us. This creates layers of temporal displacement that challenge our basic intuitions about space and observation. We don't just see the past when we look at distant objects. We see the past from locations those objects have since vacated. As you listen, notice how this transforms the meaning of astronomical observation. Every telescope image is a historical document. Every spectrum of starlight is a message from a different era. The farther we look, the deeper into cosmic history we peer. The Hubble Space Telescope has captured images of galaxies so distant that their light began its journey when the universe was less than 1 billion years old. These galaxies appear small, irregular, actively forming stars at rates much higher than modern galaxies. We're seeing cosmic adolescence, a period when the universe was more chaotic, more dynamic, fundamentally different from the mature cosmos we inhabit today. But even these ancient observations have limits. The universe was opaque for its first 380,000 years. Light couldn't travel freely through space because it was filled with ionized hydrogen that scattered photons before they could journey very far. We call this the cosmic dark age, a period hidden from direct observation. The cosmic microwave background marks the end of this dark age, the moment when the universe became transparent for the first time. This radiation fills all of space, the afterglow of the Big Bang, carrying information about conditions when the cosmos was less than 400,000 years old. But before that moment, the universe remains partially hidden from us. The very first stars, the initial formations of cosmic structure, the details of how matter organized itself in the early universe, all of this lies beyond the observational horizon created by cosmic opacity. Physics does not yet have complete answers for this hidden epoch. We can construct theoretical models, run computer simulations, make educated inferences based on the evidence we can observe. But direct observation of the universe's earliest moments remains impossible with current technology. This creates a humbling boundary to human knowledge. Despite all our sophisticated instruments, despite decades of careful measurement and analysis, there are aspects of cosmic history that remain fundamentally inaccessible to us. Not because we lack clever enough instruments, but because the physics of light propagation and cosmic expansion impose absolute limits on what can be observed from any location in the universe. The speed of light doesn't just limit how fast we can travel, it limits how much we can know. But there's something beautiful about these limitations. They remind us that the universe is larger than our capacity to fully comprehend it. They preserve mystery at the heart of scientific inquiry. They ensure that there will always be questions that push at the boundaries of human understanding, and they reveal something profound about the nature of information itself. In our daily lives, we're accustomed to near instantaneous access to information. We can video call someone on the other side of the planet and see their face in real time. We can access vast databases of human knowledge with a few keystrokes. Information feels abundant, immediate, always available. But on cosmic scales, information becomes precious. It must travel across vast distances at the ultimate speed limit. It arrives delayed, redshifted, so attenuated by the journey. Some information never arrives at all, lost to cosmic expansion or trapped behind event horizons. This scarcity of information shapes everything about how astronomy works as a science. Astronomers must extract maximum knowledge from every photon that reaches their instruments. They must infer the properties of entire stellar systems from subtle variations in brightness. They must deduce the composition of distant atmospheres from the precise wavelengths of light that are absorbed or emitted. The science becomes a kind of cosmic archaeology, piecing together the history and structure of the universe from fragmentary evidence scattered across space and time. Consider what astronomers can learn from a single photon that has traveled billions of light years to reach Earth. That photon carries information about the temperature of the star that emitted it, encoded in its wavelength. It carries information about the elements present in any atmosphere it passed through, recorded as absorption lines in its spectrum. It carries information about the motion of its source, preserved in its Doppler shift. It even carries information about the gravitational fields it encountered during its journey, subtly recorded in the path it took through curved spacetime. One photon, one quantum of light, billions of years of travel, multiple layers of encoded information about cosmic conditions across vast ranges of space and time. This is what makes astronomy both frustrating and extraordinary. The laboratory is the entire universe, but the laboratory exists in the past. The experiments have already been run, but the results take eons to arrive. The data is incredibly rich, but it's also incredibly sparse, scattered across cosmic distances that challenge our ability to collect and interpret it. And yet, despite these constraints, we've managed to construct a remarkably detailed picture of cosmic history and structure. We know that the universe began in a hot, dense state approximately 13.8 billion years ago. We know that it has been expanding and cooling ever since. We know that the first stars formed a few 100 million years after the beginning, and that these stars created the heavy elements necessary for planets and life. We know that galaxies formed and evolved over billions of years, that they cluster into groups and superclusters, that they're arranged in vast filaments separated by nearly empty voids. We know that the expansion of the universe is accelerating, driven by something we call dark energy, but don't yet understand. We know that most of the matter in the universe is dark matter, detectable only through its gravitational effects. This knowledge comes entirely from careful analysis of ancient light, traveling across distances measured in light years, carrying messages from across the cosmos and across cosmic time. But perhaps the most remarkable thing about this cosmic messaging system is how it connects us to the universe's history. The iron in your blood was forged in the nuclear furnace of a star that exploded billions of years ago. The calcium in your bones was created in stellar fusion reactions that occurred when the universe was much younger. The oxygen you breathe was produced by ancient stars and scattered into space by supernova explosions. You are made of stellar material, atoms that were cooked in stellar cores, blasted into space by stellar death, then gathered by gravity into new stars and planets over cosmic time. Your existence depends on multiple generations of stellar evolution, on the nuclear physics of massive stars, on the cosmic recycling of matter across billions of years. This isn't metaphorical, this is literal. The atoms in your body have traveled across the galaxy over cosmic time. They've been inside multiple stars, scattered through interstellar space, incorporated into planets, and eventually assembled into the complex chemistry that makes your existence possible. When you look up at the night sky, you're not just observing distant objects, you're looking at your cosmic ancestry. The stars you see are similar to the ones that created the elements in your body. The galaxies you observe contain billions of stars, like the ones that contributed to your atomic composition. You are connected to the cosmos, not just through the light that reaches your eyes, but through the very substance of your being. You are a temporary arrangement of atoms that have been cycling through the universe for billions of years, that will continue cycling long after your brief moment of consciousness ends. This connection operates across light-year distances and billion-year timescales. It links your moment of existence to the cosmic processes that have been operating since the first stars formed. It makes you a participant in cosmic evolution, not just an observer of it. The light year, that simple unit of distance, becomes a measure of this deep connection. It quantifies not just the space between you and the stars, but the pathways along which matter and energy have flowed to create the conditions for your existence. This perspective transforms how you might think about cosmic distances. They're not just empty spaces to be crossed. They're the medium through which cosmic evolution operates. They're the intervals across which matter cycles from star to star, from generation to generation of stellar formation. They're the distances that information must travel to connect different parts of the universe into a coherent, evolving whole. As you listen, you might notice how this reframes your relationship to cosmic scale. The vast distances that initially seemed like barriers, obstacles to human exploration and understanding, become instead the infrastructure of cosmic connection. The light years that separate us from other stars are the same distances across which stellar material has traveled to reach us. The cosmic expansion that carries distant galaxies beyond our reach is the same process that created the space within which cosmic evolution could unfold. The universe's immensity isn't separate from your existence. It's the precondition for it. Without those vast distances, without those billion-year timescales, without the slow circulation of matter through cycles of stellar birth and death across light-year scales, the complex chemistry necessary for life could never have developed. You exist because the universe is vast. Your consciousness is possible because cosmic processes operate across distances and timescales that dwarf human experience. The atoms that make up your brain, the neurons that generate your thoughts, the very capacity for awareness itself, all depend on cosmic evolution operating across light-year distances over billion-year timescales. This remains an open question in science, but current models suggest that consciousness might be one of the rarest phenomena in the universe. Stars are common, planets are common, even the basic chemistry of life might be relatively common. But the specific conditions that allow matter to organize itself into complex, self-aware systems might be extraordinarily rare. If this is true, then consciousness represents a remarkable convergence of cosmic processes, stellar evolution creating heavy elements, planetary formation organizing those elements into complex chemistry, billions of years of evolution selecting for information processing capabilities. All of this unfolding across cosmic scales, connected by light-year distances, dependent on the vast infrastructure of space and time. You might be one of the universe's rare experiments in self-awareness, a temporary arrangement of stellar material that has developed the capacity to contemplate its own cosmic origins, a brief flowering of consciousness in a universe that is mostly empty space and dark matter, where light travels for years or centuries or millennia between one organized system and another. This possibility doesn't make you central to the cosmic story. The universe would continue its evolution with or without consciousness, would keep expanding and cooling, would keep cycling matter through generations of stellar formation, regardless of whether any aware observers existed to witness it. But it does make consciousness precious in a way that transcends everyday concerns. If aware beings are rare in the cosmos, then every moment of consciousness, every capacity for wonder and understanding represents something genuinely unusual in the universe's evolution, and it makes the questions raised by light years more than academic curiosities. They become questions about the nature and rarity of your own existence, about the cosmic conditions that make awareness possible, about your place in the vast hierarchy of scales that stretches from subatomic particles to the observable universe itself. The distances measured in light years aren't just spaces between objects, they're the intervals across which cosmic evolution operates to create the conditions for matter to become self-aware. They're part of the deep structure of reality that makes your existence possible. When you consider a light year as 9.46 trillion kilometers, you're not just contemplating a large distance, you're contemplating the cosmic infrastructure within which consciousness can emerge. The vast scales that initially seem to diminish human significance become instead the foundation for that significance. The universe had to be this large, had to operate across these timescales, had to evolve through these vast cycles of stellar formation and death for you to exist as a conscious being capable of wondering about light years in the first place. This is perhaps the deepest lesson that light years teach. They reveal not just the scale of the cosmos, but the cosmic scale necessary for consciousness. They show how your awareness depends on processes that operate across distances and timescales that challenge human comprehension. They connect your moment of consciousness to the deepest structures of space and time. The light year becomes a bridge between the intimate scale of your thoughts and the cosmic scale of the universe that created the conditions for those thoughts to exist. It measures both the distance to the stars and the pathways through which stellar material traveled to become you. In a universe where distance and time are inseparable, where space and consciousness are connected through the cycling of matter across cosmic scales, the light year emerges as more than a unit of measurement. It becomes a way of understanding your place in the cosmic story, your connection to the vast processes that have been unfolding across billions of years to create this moment of awareness. The stars are not just far away, they are part of you, and the light years that separate you from them are part of the deep structure that makes your existence possible. This understanding doesn't resolve the questions raised by cosmic scale. It deepens them. It transforms them from questions about distance into questions about the nature of consciousness itself, about the cosmic conditions that allow matter to become aware of its own existence. These questions don't have complete answers yet. Physics does not yet understand consciousness. Astronomy cannot yet determine how common or rare aware beings might be in the universe. The connection between cosmic evolution and the emergence of consciousness remains one of the deepest mysteries in science. But the questions themselves are worth contemplating. They arise naturally from taking light years seriously, from following the implications of cosmic distance and cosmic time to their logical conclusions about the nature of existence itself. You don't need to fully grasp these implications. Just let them settle for a moment. Let them change how you think about the night sky, about the vast distances between stars, about your own brief moment of consciousness in a universe measured in light years. The cosmos is stranger than our intuitions suggest, more connected than its vast distances would seem to allow, more intimately related to your existence than the scale differences would seem to permit. Light years measure not just distance, but the deep architecture of a universe capable of becoming aware of itself. And this leads us to one of the most unsettling discoveries about light years and cosmic communication. The universe isn't just expanding, it's accelerating its expansion. For billions of years after the Big Bang, gravity was gradually slowing the cosmic expansion, as you might expect. All that matter, pulling on all other matter, should naturally decelerate the stretching of space. But around 5 billion years ago, something changed. The expansion began speeding up instead of slowing down. We call this accelerating force dark energy, though the name reveals our ignorance more than our understanding. Dark energy makes up roughly 68% of everything in the universe. It's the dominant component of reality, and we have no idea what it is. Current models suggest that dark energy is a property of empty space itself. The vacuum isn't truly empty. It seethes with quantum fluctuations, particle pairs popping into existence and annihilating almost instantly. These quantum processes might create a subtle but persistent pressure that pushes space apart. But this explanation raises more questions than it answers. Why would quantum vacuum energy manifest as cosmic acceleration? Why did dark energy become dominant relatively recently in cosmic history? Why is its strength exactly what we observe, rather than enormously larger or smaller? Physics does not yet have complete answers to these questions. Dark energy remains one of the deepest mysteries in science, a reminder that most of the universe operates according to principles we don't understand. The acceleration creates a cruel irony for cosmic communication. Just as the universe becomes old enough for complex life to emerge, for intelligence to develop, for civilizations to potentially arise, it begins accelerating the very expansion that isolates those civilizations from each other. Galaxies that are currently visible will eventually disappear beyond our cosmic horizon, not because they're destroyed, but because space expands faster than their light it can travel toward us. The universe is actively erasing its own contents from our observational reach. In the far future, perhaps 100 billion years from now, observers in our galaxy would see a much emptier cosmos. Most other galaxies would have been carried beyond the cosmic horizon. The night sky would be nearly dark, containing only the gravitationally bound galaxies in our local group. Those future astronomers would have no way to discover that the universe was once filled with billions of other galaxies. They would have no access to the cosmic microwave background, which would have been redshifted beyond detectability. They would have no evidence for the Big Bang, no way to measure cosmic expansion, no clues about dark energy or dark matter. The universe would appear static, small, and mostly empty. Everything we've learned about cosmic history and structure would be observationally inaccessible to them. This creates a sobering possibility. We might be living in a special time, a brief window when the universe reveals its structure and history to careful observers. Past and future civilizations might not have the same access to cosmic knowledge that we enjoy today. The accelerating expansion doesn't just limit space travel, it limits knowledge itself, gradually erasing the evidence that allows us to understand our cosmic context. As you listen, notice how this transforms the meaning of our current observations. Every telescope image, every measurement of cosmic distance, every detection of gravitational waves or cosmic microwave background radiation might represent information that will eventually become inaccessible to future observers. We're not just exploring space, we're documenting the universe during one of the few epochs when its full structure and history remain visible. This urgency operates on cosmic timescales, not human ones. The observational windows we're discussing will remain open for billions of years, but the principle remains profound. The universe's accelerating expansion ensures that cosmic knowledge has an expiration date. The concept challenges our assumptions about the persistence of information. In human experience, knowledge tends to accumulate over time. Libraries grow, databases expand, future generations have access to more information than previous ones. But on cosmic scales, the opposite might be true. Future civilizations might have access to less information about the universe than we do today. The acceleration of cosmic expansion gradually erases the evidence that allows us to understand cosmic history and structure. This doesn't make current cosmological research futile. If anything, it makes such research more important. We might be the universe's only opportunity to understand itself during this observational window. The possibility raises fascinating questions about the nature of cosmic knowledge. Is there something special about our current epoch that allows the universe to be comprehensible? Or are we simply lucky to exist during a brief period when cosmic structure remains visible? Some physicists have speculated that the emergence of consciousness and the visibility of cosmic structure might be connected. Perhaps intelligence naturally arises during the cosmic epoch when the universe is most comprehensible. Perhaps consciousness is the universe's way of understanding itself before accelerating expansion erases the evidence of its own history. This remains speculative, but the timing is intriguing. Complex life emerged relatively late in cosmic history, just as dark energy was becoming dominant. Intelligence developed just as the universe was beginning to accelerate its expansion most dramatically. The correlation might be coincidental, or it might reflect deeper connections between cosmic evolution and the emergence of awareness that physics does not yet understand. Current models suggest that consciousness requires specific cosmic conditions. Stars must have had time to create heavy elements through nuclear fusion. Those elements must be scattered by supernova explosions and incorporated into new stellar systems. Planets must form and evolve stable conditions over billions of years. All of this requires a universe old enough for multiple generations of stellar evolution, but not so old that star formation has ceased. It requires cosmic expansion to create the space within which structure can form, but not expansion so rapid that structure cannot form at all. The window for consciousness might be naturally limited, too early, and the universe lacks the heavy elements necessary for complex chemistry. Too late, an accelerating expansion might prevent the formation of new stars and planets. We might exist during the universe's brief flowering of complexity, its narrow window of conditions suitable for the emergence of awareness. This possibility doesn't make consciousness central to cosmic evolution. The universe would continue expanding and cooling, regardless of whether any aware observers existed to witness it. Stars would continue burning, black holes would continue evaporating, entropy would continue increasing according to the laws of thermodynamics. But it does suggest that awareness might be temporally as well as spatially rare. not just uncommon in any given region of space, but uncommon in any given epoch of cosmic history. If this is true, then every moment of consciousness represents something genuinely unusual in the universe's evolution. Every capacity for wonder, every scientific discovery, every instance of awareness contemplating its own cosmic context might be precious precisely because such moments occur only during a narrow window of cosmic time. The light years that separate potential civilizations become not just spatial distances, but temporal ones. Even if intelligent life emerges independently in multiple locations, those civilizations might be separated by cosmic epochs as well as cosmic distances. Two civilizations separated by 1,000,000 light years might also be separated by millions or billions of years in time. One might emerge and flourish and disappear long before the other develops the capacity for cosmic observation. The universe might be filled with intelligence across its history, but that intelligence might never overlap temporally in ways that allow communication or mutual recognition. This temporal isolation operates in addition to the spatial isolation created by light travel time. Even if we detected signals from an extraterrestrial civilization, those signals would carry information about that civilization's distant past. By the time we received their transmission, they might have evolved beyond recognition or ceased to exist entirely. And our reply, traveling at light speed across cosmic distances, would reach their location long after our own civilization had changed in ways we cannot predict. The universe's vast scales create multiple layers of isolation: spatial isolation due to light travel time, temporal isolation due to the brief windows suitable for complex life, observational isolation due to accelerating cosmic expansion. These forms of isolation might ensure that consciousness, however common it might be across cosmic history, remains fundamentally alone in its immediate experience. Each aware civilization becomes a brief experiment in cosmic self-understanding, arising during the narrow window when the universe is old enough to support complexity, but young enough to remain comprehensible. You don't need to find this prospect depressing. There's something beautiful about the idea that consciousness might be the universe's way of experiencing wonder at its own structure and history, even if that wonder occurs in isolation across vast distances of space and time. Every moment of awareness becomes a rare convergence of cosmic conditions. The heavy elements in your brain were forged in stellar cores across billions of years. The stable orbit of your planet was established through gravitational interactions operating over cosmic timescales. The complex chemistry of your neurons depends on quantum mechanics operating at subatomic scales. Your capacity to contemplate light years emerges from processes spanning the full hierarchy of cosmic scales, from quantum fluctuations to galactic evolution. The isolation imposed by cosmic distances doesn't diminish this achievement. If anything, it makes awareness more remarkable. In a universe where information travels slowly, where civilizations are separated by light years and cosmic epochs, where accelerating expansion gradually erases the evidence of cosmic history, the mere existence of consciousness becomes extraordinary. The fact that matter can organize itself into configurations capable of understanding light years, cosmic expansion, stellar evolution, and quantum mechanics represents one of the universe's most improbable accomplishments. This understanding doesn't resolve the loneliness imposed by cosmic scale. It reframes that loneliness as a consequence of rarity rather than insignificance. If consciousness is common in the universe, then the isolation created by light-year distances becomes a tragedy of cosmic proportions. Countless civilizations existing in mutual ignorance, separated by distances and timescales that prevent communication or collaboration. But if consciousness is genuinely rare, then that same isolation becomes part of what makes each instance of awareness precious. The vast empty spaces measured in light years become the necessary context within which something as improbable as consciousness can emerge and flourish briefly, before cosmic expansion carries everything beyond the reach of observation. The universe had to be this large, had to evolve across these timescales, had to operate according to physical laws that impose these speed limits and distance scales for you to exist as a conscious being capable of contemplating its own cosmic context. The light years that initially seemed to diminish human significance become instead part of the cosmic infrastructure that makes that significance possible. This is perhaps the strangest lesson that emerges from taking light years seriously. The vast scales that challenge human intuition, that make space travel impractical and cosmic communication nearly impossible, are also the scales necessary for consciousness to emerge in the first place. You exist because the universe is measured in light years. Your thoughts depend on cosmic processes operating across distances that dwarf everyday experience. Your awareness emerges from the same physical laws that govern stellar evolution, galactic formation, and the expansion of space itself. The cosmos is not indifferent to consciousness. It's the precondition for consciousness. But that doesn't make consciousness essential to cosmic evolution. It makes cosmic evolution central to consciousness. Every light year represents not just distance, but the cosmic infrastructure within which matter can become aware of its own existence. The vast scales measure the pathways along which stellar material has traveled to become organized into the complex chemistry of your brain. When you contemplate a light year, you're contemplating the cosmic conditions that make contemplation possible. When you wonder about the distances between stars, you're experiencing the universe's capacity to understand itself through the temporary arrangements of matter we call conscious beings. This doesn't solve the mystery of consciousness. Physics does not yet understand how matter gives rise to awareness, how quantum processes in neurons create the subjective experience of being you, how the universe becomes capable of contemplating its own existence. But it does place that mystery in cosmic context. Consciousness emerges not despite the universe's vast scales and slow processes, but because of them. The light years that separate stars are part of the deep structure that makes awareness possible. The universe is stranger than we imagine, not just because of its size, but because its size is intimately connected to the possibility of understanding that strangeness. Current measurements suggest the observable universe contains roughly 2 trillion galaxies. Each galaxy contains billions or trillions of stars. The total number of stars in the observable universe approaches a number so large that counting them would take longer than the universe has existed. And somewhere in that vast collection, matter has organized itself into configurations capable of measuring cosmic distances, detecting gravitational waves from colliding black holes billions of light years away, mapping the cosmic microwave background radiation and contemplating the nature of consciousness itself. The probability of this occurring in any particular location might be vanishingly small, but the universe is so large that even vanishingly small probabilities can manifest somewhere within its vast expanse. You might be the universe's rare experiment in self-awareness, a brief flowering of consciousness in a cosmos that is mostly empty space, dark matter, and dark energy, where light travels for years between organized systems, where matter cycles through generations of stellar evolution across billion-year timescales. This possibility doesn't make you the center of the cosmic story, but it does make your existence genuinely remarkable in ways that transcend everyday concerns about significance and meaning. The questions raised by light years become questions about the cosmic conditions necessary for those questions to arise in the first place. The vast distances that challenge human intuition become part of the explanation for why human intuition exists at all. As you listen, let these scales settle without trying to fully grasp them. Let the connections between cosmic distance and consciousness remain mysterious rather than resolved. Let the universe remain larger than your capacity to comprehend it completely. The beauty of light years lies not in understanding them perfectly, but in recognizing how they connect your moment of awareness to the deepest structures of space and time. You don't need to hold 9.46 trillion kilometers in your mind as a concrete distance. You just need to recognize that this distance measures something more than empty space between objects. It measures the cosmic architecture within which consciousness can emerge, the pathways along which stellar material travels to become organized into complex chemistry, the scales across which information must flow for the universe to develop the capacity to understand itself. The light year becomes a bridge between the intimate scale of your thoughts and the cosmic scale of the processes that created the conditions for those thoughts to exist. In a universe where distance and time are inseparable, where matter and consciousness are connected through cycles of stellar evolution operating across cosmic scales, where awareness emerges from the same physical laws that govern the expansion of space itself, every moment of consciousness becomes a remarkable convergence of cosmic conditions. The stars are not just far away. They are part of the deep history that makes your awareness possible. And the light years that separate you from them measure not just distance, but the cosmic infrastructure that allows matter to become conscious of its own existence. This understanding transforms rather than resolves the questions raised by cosmic scale. It connects your brief moment of consciousness to the vast processes that have been operating across billions of years to create the conditions within which consciousness can emerge. The universe becomes not just the container within which you exist, but the necessary precondition for your existence. The cosmic distances that initially seem to diminish human significance become instead part of the explanation for why significance is possible at all. Light years measure both the distance to the stars and the cosmic pathways through which stellar material has traveled to become you. And yet, even as we contemplate this cosmic loneliness, there's another layer of strangeness waiting in the darkness between stars. Because when we measure distances in light years, we're not just measuring empty space. we're measuring something that physics is still struggling to understand. The space between galaxies isn't actually empty. It's filled with dark matter, a substance that makes up roughly 27% of everything in the universe, yet remains completely invisible to our instruments. Dark matter doesn't emit light. It doesn't absorb light. It doesn't reflect light. We know it exists only because of its gravitational effects on the matter we can see. When astronomers measure how fast stars orbit around galactic centers, the numbers don't add up. The stars are moving too quickly. Based on the visible matter alone, those stars should fly off into space. Something invisible must be holding them in their orbits. Something with mass, but without any interaction with electromagnetic radiation. Computer simulations suggest that dark matter forms a vast scaffolding throughout the universe. Invisible filaments stretching across hundreds of millions of light years, creating the framework upon which visible galaxies form. The cosmic web we observe in the distribution of galaxies might be just the visible tip of a much larger, invisible architecture. As you listen, notice how this transforms our understanding of cosmic distances. When light travels across billions of light years, it's not journeying through empty space. It's passing through invisible matter whose nature remains mysterious. The universe is filled with substance we cannot detect directly, organized into structures we cannot see. This invisible scaffolding might dwarf the visible universe in both mass and complexity. The galaxies, stars, and planets that seem to fill the cosmos might represent only a small fraction of what actually exists. Most of reality might be hidden from us, detectable only through its gravitational influence on the small portion of the universe that emits light. Current models suggest that for every kilogram of ordinary matter, there are roughly 5 kilograms of dark matter. The universe is dominated by substance that remains completely mysterious. We live in a cosmos where most of what exists operates according to principles we don't understand. The search for dark matter represents one of the most intensive efforts in modern physics. Deep underground laboratories house detectors designed to catch dark matter particles colliding with ordinary atoms. Particle accelerators attempt to create dark matter in high-energy collisions. Space-based telescopes map its distribution through gravitational lensing effects. So far, these efforts have yielded tantalizing hints, but no definitive detection. Dark matter remains stubbornly hidden, present everywhere yet accessible nowhere. Its existence is certain. Its nature remains completely unknown. This uncertainty pervades our understanding of cosmic distances. When we say a galaxy is 10 billion light years away, we're describing the path that light has taken through a universe filled mostly with invisible matter. That light has been traveling through dark matter scaffolding, past dark matter clumps, around dark matter concentrations that bend space-time in ways we can measure but not directly observe. The cosmic architecture revealed by light-year measurements might be only a shadow of the actual architecture that exists. The real universe, dominated by dark matter and dark energy, might be far stranger and more complex than anything visible light can reveal. But there's something even more unsettling about these cosmic distances. They're not just measurements of space, they're measurements of time. And time itself might not be what our everyday experience suggests. Einstein's relativity revealed that time passes differently depending on your motion and your location in gravitational fields. Time dilation isn't just a curious effect that shows up in precise measurements. It's a fundamental feature of reality that becomes dramatic under extreme conditions. Near the event horizon of a black hole, time slows dramatically relative to distant observers. An astronaut falling into a black hole would experience time passing normally from their perspective. But to someone watching from a safe distance, that astronaut would appear to slow down, their movements becoming more and more sluggish as they approach the horizon, their image redshifting and fading, but never quite disappearing from view. This isn't an optical illusion. Time genuinely passes at different rates in different locations. The astronaut's watch would tick normally from their perspective, but those ticks would be stretched out across longer and longer intervals as measured by the distant observer. When we measure cosmic distances in light years, we're implicitly assuming that time passes uniformly throughout the universe. But this assumption breaks down near massive objects in regions of strong gravitational fields, or for observers moving at high speeds relative to the cosmic microwave background. A civilization orbiting close to a massive black hole would experience time very differently than we do. Their years would be longer than ours when measured by cosmic standards. Their biological processes, their technological development, their entire temporal experience would be stretched relative to civilizations in less extreme gravitational environments. Light years become a more complex measurement when you consider these relativistic effects. The distance light travels in 1 year depends on whose year you're measuring, whose clocks you're using, whose frame of reference defines simultaneous events across cosmic distances. This temporal complexity adds another layer of isolation to cosmic communication. Even if we could somehow send messages faster than light, which current physics suggests is impossible, the synchronization of time across cosmic distances remains problematic. Events that appear simultaneous to one observer might be separated by years or centuries for an observer in a different gravitational field or moving at a different velocity. The universe doesn't provide a universal clock that all observers can agree upon. Time itself becomes relative, stretched and compressed by gravity and motion in ways that make cosmic coordination extraordinarily difficult. Consider what this means for our observations of distant galaxies. When we see a galaxy as it appeared 10 billion years ago, we're seeing it in its own temporal frame, not ours. The billion-year processes we observe in that galaxy might have unfolded at rates very different from what we experience locally, depending on the gravitational environment and relative motions involved. The cosmic history we reconstruct from ancient light might be more complex than a simple timeline suggests. Different regions of the universe might have experienced cosmic evolution at different rates, with gravitational time dilation creating temporal variations across cosmic scales. Physics does not yet have a complete framework for understanding how consciousness might relate to these temporal complexities. If awareness emerges from processes that depend on precise timing, on synchronized neural activity, on information processing that unfolds at specific rates, then the relativistic nature of time adds another constraint to the conditions necessary for complex life. Consciousness might require not just the right chemical elements, the right planetary conditions, the right stellar environment, but also the right temporal environment. Regions of spacetime where time passes at rates compatible with the information processing requirements of complex neural systems. This temporal constraint might make consciousness even rarer than purely spatial considerations would suggest. Not only must the right conditions for complex chemistry emerge in the right place, they must emerge in regions of space-time where time passes at rates suitable for the development and maintenance of aware beings. The vast majority of the universe might be temporally unsuitable for consciousness, even if it contains all the necessary chemical ingredients. Near black holes, in regions of extreme gravitational fields, or for systems moving at significant fractions of light speed, the temporal environment might be incompatible with the precise timing requirements of neural activity. You don't need to fully grasp these temporal complexities. Just let them remind you that the universe revealed by light-year measurements might be even stranger than distance alone suggests. Time itself becomes relative, stretched, and compressed across cosmic scales in ways that challenge our basic intuitions about simultaneity and duration. The cosmic distances that separate potential civilizations aren't just spatial barriers, they're temporal barriers, regions where time itself flows at different rates, where the synchronization necessary for communication becomes problematic even in principle. This doesn't make cosmic communication impossible, but it does make it far more complex than simple distance calculations would suggest. The universe imposes multiple layers of isolation, spatial separation requiring light travel time, temporal separation due to relativistic effects, and the ongoing expansion of space that carries distant objects beyond observational reach. These isolation mechanisms might ensure that consciousness, however common it might be across cosmic history, remains fundamentally alone in its immediate temporal experience. Each aware civilization exists in its own bubble of spacetime, connected to the rest of the universe only through ancient light carrying information about events that occurred in different temporal frames under different gravitational conditions. The light years that measure cosmic distances also measure the complexity of cosmic time, the relativistic effects that make the universe temporally as well as spatially vast. They reveal a cosmos where space and time are woven together in ways that create barriers to communication and understanding that go far beyond simple distance. But perhaps the most profound implication of these cosmic scales emerges when we consider what they suggest about information itself. In our daily experience, information feels abundant and immediate. We can access vast databases of knowledge, communicate instantly across continents, record and preserve thoughts and images with remarkable fidelity. But on cosmic scales, information becomes precious in ways that challenge these everyday assumptions. Information must travel at the speed of light, the ultimate speed limit for causal influences. It becomes stretched by cosmic expansion, redshifted by gravitational fields, delayed by the vast distances between organized systems. Most profoundly, information can be lost entirely. Black holes represent regions where information disappears beyond any possibility of retrieval. The event horizon marks a boundary beyond which no information can ever return to the outside universe. Whatever falls past that boundary is lost to external observers forever. This creates what physicists call the information paradox. Quantum mechanics suggests that information cannot be destroyed, only scrambled or transformed. But general relativity suggests that black holes can permanently remove information from the universe. The two fundamental theories of modern physics give contradictory answers about what happens to information that crosses an event horizon. Current research explores various possibilities. Perhaps information is encoded at the event horizon itself, preserved in subtle correlations that are gradually released as the black hole evaporates through Hawking radiation. Perhaps space-time itself breaks down at the quantum scale, and our classical concepts of information preservation don't apply in such extreme environments. But the paradox remains unresolved, a reminder that our understanding of information, consciousness, and cosmic communication operates at the boundaries of known physics. The universe might destroy information, preserve it in forms we don't recognize, or transform it according to principles we haven't discovered yet. This uncertainty permeates every aspect of cosmic communication. When we send radio signals into space, hoping to contact extraterrestrial civilizations, we're betting that information can survive journeys across light-year distances, that it can be preserved and decoded by recipients whose information processing systems might operate according to principles very different from our own. We're assuming that the patterns we consider meaningful would remain meaningful after traveling for years or centuries through the vacuum of space, through gravitational fields that bend space-time, through cosmic expansion that stretches wavelengths and reduces signal strength. These assumptions might be reasonable for nearby targets, but they become increasingly questionable for truly distant destinations. Information that travels across billions of light years must survive not just the journey through space, but the evolution of the universe itself during that travel time. A signal sent to a galaxy 10 billion light years away would arrive at a cosmic epoch very different from our own. The universe will have expanded significantly. Star formation rates will have changed. The cosmic microwave background will have cooled and redshifted. The very conditions that we consider normal for information processing might no longer exist. Any civilization capable of receiving such a signal would be operating in a universe substantially different from the one that sent it. Their information processing systems, their understanding of physics, their technological capabilities would all have developed under cosmic conditions that we cannot predict or imagine. The possibility of meaningful communication across such distances and timescales becomes questionable not just because of travel time, but because of the fundamental changes that occur in cosmic conditions over the periods required for such communication. As you listen, consider how this transforms our understanding of cosmic loneliness. We might be isolated not just by distance and time, but by the very nature of information itself in an expanding, evolving universe where the conditions suitable for complex information processing might be rare and temporary. The search for extraterrestrial intelligence becomes not just a search for other conscious beings, but a search for other conscious beings who exist under similar cosmic conditions, who process information in ways compatible with our own, who live in regions of space-time where meaningful communication remains possible. The requirements for cosmic communication might be far more restrictive than simple distance calculations suggest. Not only must consciousness emerge independently in multiple locations, it must emerge under conditions that allow for mutual comprehension and information exchange across the vast scales of space and time. The light year reveals itself not as a simple measurement, but as a window into the deepest architecture of existence. 9.46 trillion kilometers becomes more than distance. It becomes the scale at which space and time weave together, where matter cycles through cosmic evolution, where information travels between islands of complexity separated by vast oceans of emptiness. When you look up tonight, you're not just seeing distant stars, you're seeing the pathways along which the atoms in your body once traveled. You're witnessing the cosmic infrastructure that makes consciousness possible. You're observing a universe that had to be exactly this large, exactly this old, exactly this strange, for matter to organize itself into configurations capable of contemplating light years. The cosmic loneliness imposed by these distances isn't a flaw in the universe's design. It's a feature of the same processes that allow awareness to emerge at all. The isolation created by light travel time, by relativistic effects, by cosmic expansion, might be the necessary context within which something as improbable as consciousness can briefly flourish before the expanding darkness carries everything beyond reach. Physics does not yet understand how matter becomes aware of itself, how quantum processes and neural networks give rise to the subjective experience of wondering about cosmic distances. But it does reveal that consciousness, if it exists elsewhere, faces the same fundamental barriers we do, the same speed limits, the same temporal complexities, the same information constraints that make communication across light years not just difficult, but perhaps impossible in any meaningful sense. We might be alone not because consciousness is unique to Earth, but because the universe's structure ensures that all conscious beings remain isolated in their own bubbles of space-time, connected only through ancient light, carrying messages from epochs when cosmic conditions were different. This isolation doesn't diminish consciousness, it makes it precious. Every moment of awareness becomes a rare convergence of cosmic processes operating across scales that challenge human comprehension. Every capacity for wonder, every scientific discovery, every instance of matter contemplating its own cosmic origins represents something genuinely extraordinary in a universe measured in light years. The stars are not just far away, they are part of the deep history that makes your awareness possible. And the light years that separate you from them measure not just distance, but the cosmic pathways through which stellar material has traveled to become organized into the complex chemistry of consciousness itself. In a universe where distance and time are inseparable, where information travels slowly across vast emptiness, where consciousness might be temporally as well as spatially rare, every moment of contemplation becomes a remarkable achievement. The universe becomes aware of itself through brief arrangements of matter that can measure cosmic distances, detect gravitational waves from colliding black holes billions of light years away, and wonder about their own place in the cosmic story. Light years measure both the vastness that humbles us and the cosmic architecture that makes humility possible.